you don't really need to memorize it, because when I give you the exam, I will give you the equations. However, when I give you the exam, I usually don't tell you which equation is which one. What does that mean? Let me show you an example. Let me show you one example. Not this one. Maybe exam 2. Like, this is one problem where you will see the details in first. Then I will show you a bunch of equations. But I actually scramble them, move around, randomize the position, so you cannot just easily realize which one is which. So at least you need to, when you see this, you should know, okay, this is maximum strain energy model. When you see this one, okay, maximum distortion energy model. For example, if you see this one, this is the first principal stress for general case, the second principal stress for principal case, shear stress, normal stress, maximum shear model, things like that. You need to recognize, okay, that one is which model, which equation. So when you solve the problem, these are reminders for you. But I don't want to directly tell you, because if you know the equation, all you need to do is plug in numbers. Not very difficult. That's why I will provide some help, but you need to realize how which one is for what. Okay? So maybe do I need to quickly review the two models? Just very quickly, okay? I'm not going through the mathematics in detail. I'm gonna just quickly talk about it. Okay, so in that case, can maybe I download it. So for strain energy model, what happened was we built up a scenario to represent general cases on a small piece of material. So all kinds of cases can reduce to a general case like this. And you can have principal stress directions. Based on what we learned from Moore circle analysis, we know if we change how we observe the material, there is always one orientation where you only have normal stress. So this is a general case. We only have normal stress. So basically principal stress directions. In this case, we have some simple equations for solid mechanics elastic mechanics, and we want to analyze the strain energy. What is strain energy? If you have a material, you deform the material by doing some work. So, as if this is a spring, if you compress it, you need to do some work to compress it. And in ideal world, all the work you have done will be stored inside the elastic material, inside the spring. And if you release it, you will return back to original shape. So strain energy basically is the energy that is stored inside the material. So we want to calculate if a material is being deformed by multiple stress forces, what's the strain energy that is stored inside the material? Okay, so after a certain derivation, we found, okay, this is the total strain energy. However, when we define this model, we didn't mention what's the dimension of it. We only put a symbol. That's why in the next page, we would like to study in a normalized unit. So we divide the total strain energy by the total volume. So at the end, we have strain energy per unit volume. Okay, it's a more it's a more standardized, normalized unit. After we do that, we can observe what we have right here. This equals to only U can be defined by several things only. One is material property. This is Young's modulus, and also Poissons ratio, also material property. The other one is the force. How much stress you have along each direction, and they will be formulated in this equation. Then you can calculate the strain energy. Okay, if there's no force, no deformation, no strain energy. If there's only one force along one direction, then we have an equation like this, because the stress along y and z are 0. So for a general case, a tensile test, we only have stress in, for example, x direction. And we use the idea where tensile test will lengthen the material until it yields. So when we reach the limit of the material, the strain energy will equal to this, because this is where your stress equals to yield strength. So we use this trick to determine how much strain energy this material can store. If you press a little bit more or pull a little bit more to generate more deformation, just a little bit, the strain energy will be increased a little bit, but it will yield, because when this increased, that means you are over the limit of this material. That's why we believe this value is the upper bound, the upper limit of U. That's why this equation must be smaller than or equals to this extreme number, this limit. And that's how we get this equation right here. After that, we realize the 1 over 2e is not important. We can get rid of them. And also, we wish on the right-hand side of the equation, we don't have square. That's why we take a square root. So at the end, we have this long equation. It looks very difficult to memorize, but you don't need to. Okay, for our exam, we don't need to memorize it. Okay, this is the general equation for maximum strain energy model. You can have stress in every direction, x, y, and z. And over here, there's a unique property included in the equation. You need to know the Poissons ratio. Okay, Poisson ratio for every material cannot be 0.5. Okay, so usually this value is less than 0.5, something like 0.4, 0.3. Okay, and for plane stress problems, it reduced to this because we don't have stresses on the third direction. So this is much easier to memorize if you would like to do it. Yeah, you can memorize it. Only for plane stress problems. And if you would like to plot it out, I show a way how to plot out the figure in the video. You can watch it again. Basically, it's gonna be an ellipse with 45-degree tilting angle against the original coordinate. And it is having contact with the maximum shear stress model. So from here you can tell maximum strain energy model is an extension of maximum shear stress. It's a bigger design space. So when you have a smaller design space, you're more conservative. When you have a larger one, you are less conservative. You want to take a risk when you use maximum strain energy. Okay? This is where, this is what you get if you apply safety factor at the bottom of the right hand side. Then this is how it look like. So quickly review the other one. This video could be difficult to understand, this part. What is distortion? So when people define distortion, it means a kind of deformation that doesn't cause volume change. Okay, and we call it distortion. But for general loading condition, you could be shrinking the material or stretching the material. When you shrink or stretch the material, the volume will change. So in this general case, if we can only focus on the volume change in one part of the analysis, and for the second part, we consider that as pure distortion, no volume change, pure deformation. So it's like you have clay and you are, changing its shape, but you don't pull it. Okay. So if we can do that, we can do a bunch of mathematical derivations. This could be true when those deformations are quite small. So maybe you challenge this theory. Are you sure this is equal? Can I really do this analysis? This trick is so-called a superposition. You basically sum up multiple phenomena together, and you assume when you add them up, it should end up with something you wish, and you assume those are like an independent phenomenon, and they can be added up. How do you know if you put them together? Maybe they are dependent. Then when you add them up, it won't equals to the left-hand side. But in those kind of theory, they are all having very small deformations. So we assume this equation works. So this is an assumption. And when we have very small deformation, this should be fine. And in the video, I introduced how to analyze each terminology right here. This one we already derived in the previous the strain energy model. We already derived this. This is what we had earlier. And for this method, it's called maximum distortion energy. So it seems like we need to calculate how much strain energy due to distortion should be, how much we have for the strain energy due to distortion, right? We want to know this. But based on the assumption, based on the concept right here, it's difficult to derive this part directly. So how we calculate this was based on calculating this part first. We calculate the strain energy for pure volume change first, and then since we already know this guy, so we can just use U minus UV to get UD. This is a really unique way to derive distortion energy. So if you are interested, I hope you can watch the video again to realize the beauty of this part. When I prepared this lecture for distortion energy, it really took me some time to understand why they did it. And after several times of studying this theory and understanding the equations, I realized, okay, the main reason is just because direct derivation of this is not easy. But direct derivation of these two parts are much easier. That's why they use this assumption must be valid, and these two should be derived afterward. Then you can use U minus UV to get UD. I'm not going to go through this again, but there are some assumptions. One of the most important assumptions is this one. This is the strain in each direction of the distortion part here. If you have stress to perform distortion on this figure, if you have strain, then you must have stress. If you have stress, you must have strain. And since we have stress for distortion, but distortion means you should not have volume change, then you can kind of realize making this drawing in a specific way. When I make the Z longer and the Y longer, I need to draw the X shorter. I need to shrink X. Otherwise, this doesn't make sense because I claim there's no volume change. So somewhere has longer length, but some other places has shorter length. So the idea of zero volume change is being mathematically described as this equation. It assumes the sum of strain on each direction equals to 0. And they claim this equation is representing zero volume change for distortion. But can you truly use it to represent distortion, does it really mean no volume change? When they are very small, I think yes, we can. But if we have large deformation, how are you sure? Okay, so this is the one assumption that this theory made. Okay, and the rest are just mathematics. With certain derivation at the end, the strain energy for volume change was calculated. And since we already know strain energy, we know this, and we derive this guy, then we can calculate UD, the distortion energy. So it's a long mathematical equation, but if you are patient, you can reduce it to this guy. And we can now observe what's going on right here. In this equation, we also have Young's modulus, we also have Poissons ratio, but this time Poisson ratio is outside of the bracket. Okay? It's a little different from the other two equations. That's fine. What's next? So I think the beauty of this derivation is that it's always using tensile test to find the design limit. So no matter what you get at the end, it's an equation, it's a long equation that you really don't know what you can do afterward. But the trick for the next step is to focus on tensile test. So if this is the distortional energy, then the distortion energy for tensile test could be calculated like this. And the distortion energy when the material is about to yield, the distortion energy should equal to this. And this theory assumes this should be the maximum distortion energy the material can handle. So this is the upper limit. Therefore, at the end, this is the general distortion energy. This is the upper limit. This should be smaller than this. This is how the design equation was made. The general distortion energy for all cases should be smaller than the upper limit we calculated. And what's interesting afterward is that the coefficient cross out, and we no longer have Young's modulus and Poisson ratio in this model. So it's a model that purely represents the magnitude of stresses in each direction. So I don't know how those scientists derived this 100 years ago. I have no idea. I always think the way they derive this is so intelligent, and the result of the derivation was so clean. It's really, I feel like it's really beautiful. And maybe they have the same feeling. They realize, okay, this is truly a nice equation. We should name it. So, does anyone know when you see Van in the person's last name? Is he from which country? Italy or somewhere from in Europe, right? Or Germany? Do you know? Belgium? You sure? Okay. Somewhere in Europe. So there. I'm not the kind of researcher who likes to study the history. I don't care. But I know some professors are fascinated by the history of the research progress or how the research was developed. So I know some professor will pay a lot of attention at the first several chapters of the book because it's like a story about that history. I don't like history, so I don't usually care about who the person is, where he's from, but whenever you see a name like this, you know he's from Europe, okay? So he, maybe at some year, long time ago, this person named this, or I don't know how, this was defined as the von Mises stress. All I care about is what does it mean, okay? I think you guys should pay attention to what does it mean. So let's first take a look at the unit. This is something must be smaller than stress. So on both sides of the equation, we should have the same unit. So we should have this huge thing in the unit of stress, same unit. So this is a stress term, okay? Even we see a square root, we usually don't see a stress can be derived in a mathematical form, including square root. We usually don't see this. But the way it was, based on the way it was derived, it looks like that, okay? And then inside the square root, we have stresses along each direction. And they are being placed together in this particular format. If the stress along x is greater, this whole term is greater. Stress in y is greater, this is greater. Stress in z is greater, this is greater. Right? So it seems like this value can represent stress levels in each direction. So this is commonly used as a dimensionless stress terminology. Not dimensionless, directionless. It's a directionless. Sorry. It has no direction. So it's like the equivalent amount. Equivalent. Or you can kind of understand it as a equivalent. You can say it's like an equivalent stress. So including or addressing. Maybe use addressing is a better word. Addressing the stress conditions in all x, y, and z directions. Okay, but it doesn't tell you what's the overall direction. This term has no direction. It only tells you the total stress level, but not direction. No direction. No direction, no information for this model. So if you study, let's take a look at MSS, von Mises. Okay, just really, which one is the image? This one, Indonesian. Okay. Maybe this guy. Does it show? Too small, cannot tell. Trying to find a figure that shows here. See, it says equivalent von Mises stress, and when when you use MSS to, it's a very well-known software for stress analysis. After you define the load condition, the material property, and boundary conditions, solve, and the software will find the solution. At the end, it tells you, it gives you a color bar to represent the stress distribution everywhere. You read the color to understand how much stress you have. But the unit was in megapascal, and it's equivalent of MSE stress, no direction. So when you see, for example, there's no red. For example, here's a yellow, and let's say yellow right here. So what does it mean when you see a material has a yellow color? That means that that yellow element is under an equivalent stress of 250 megapascal, but we have no idea what's the direction of it. So how can we make sure that yellow material is within the safe region? You would just use the maximum distortion energy. So MSE stress must be smaller than yielding strength. That's it. As long as the MSE stress is not greater than yielding strength, we're okay. This is how easy we can use it. And when we use a software, when we read MSE stress, as long as it's not greater than yield strength, it's good. So why do we need to learn this course? Just use ANSYS. Yes, you're right, just use ANSYS. Because you know, for all kinds of designs, what we learn in the book, they are all in very simple geometry. But in reality, for mechanical design, it's an arbitrary shape, all kinds of shapes. How do you know how to formulate equation for that shape? You can't. It's too difficult. It's too difficult to derive the mathematics behind that arbitrary shape. So you can put it in software. So the software will cut the entire piece into small pieces. We call finite element. So we cut the software cut the whole piece into small elements and treat each element, usually treated as elastic material. So just solve elastic mechanics inside that tiny material. And you can have 10,000 materials over here, as long as every material has continuous deformation. So continuum is important. Continuum. Okay? What is continuum in Chinese? It's a mechanics that describes continuous deformation. If one material deformed this way and the item next to it deformed in the other way, they don't have continuous deformation, then it breaks, right? So for finite element, we assume continuous low conditions, continuous deformations. So that's how the software can model the whole thing. Sorry, hands are falling. Okay. So now you know this is widely used in mechanics, in the industry, in softwares, but I don't think everyone knows what barometric stress means. They just use it. I wish you know what is barometric stress. In the future, when you do research or work, I wish you know what it is. And what's behind it is something like this. It's a equivalent stress that includes information of stresses along all three directions. Okay? And when you reduce to plane stress problem, it looks like this. Very similar to the maximum strain energy model. How it look like is very similar to maximum strain energy model, but there is a slight difference. Compare them easily. The only difference is that you have 2 mu here, but this is 1 here. Okay? And we know for Poissons ratio, for materials around the world, mu cannot be 0.5. It's usually less than 0.5. So when you have 1 right here, and you compare to maximum strain energy, it seems like this model kind of like, I use kind of like because they are not the same, but you can use it to kind of memorize what's going on. So the equation over here kind of like maximum strain energy model with mu equals 2.5. And what is mu equals 0.5? This is called the ideal material. Because it doesn't happen. There's no material with mu equals to 0.5. But when you have 2 mu, and if mu is 0.5, this equals to 1, and then this equation is equals to the maximum distortion energy, right? This is how they are different. Just because in reality, no material can be having 0.5 or Poissons ratio. So this maximum strain energy model can never approach to the maximum distortion energy model. There's always a tiny gap. And this tiny gap depends on how large the Poissons ratio is. Okay, from here you can tell, I didn't talk about it in the video, but right here you can see, when I try to draw this, I need to calculate the distance right here. This distance depends on your Poissons ratio. So if this value changes, this range changes. Okay? So if a material has a has a very small Poissons ratio, which means when you stretch it, it doesn't shrink too much. If you have something like that, then this becomes greater. Okay? But if you have a material when you stretch and it shrinks a lot, and your Poissons ratio is very close to 0.5, in that case, your maximum strain energy model is very close to distortion energy model. Okay? In general, the smallest model, the model with smallest design space is maximum shear stress model. The largest one, the most aggressive one, maximum strain energy model. At the middle, maximum distortion energy model. Okay? So keep this image in your mind. Now, today I want to try to solve a problem. Because of very limited time, maybe I will solve the problem that I used in the past, maybe this one. I wanted to create a different problem, but sorry, today I don't have enough time, so let me just use this one. Okay, so this is also on the web page. But this is the same problem. It's too boring. Sorry. Let's try to study a different problem. Way too boring, sorry. I think I had maybe this problem. Yes, this is a little different. Okay, good. Download it. So I will share this one afterward. I'm sorry you don't have it. Or do you want it right now? Let me just, anyway, I will share later on. Sorry. So this one doesn't ask you to solve the stress strain problem. It directly tells you, okay, there's a small piece of the material right here, and the low condition, the low diagram looks like this, and it tells you how much bending stress it is carrying, and also how much twisting moment, a bending moment and twisting moment, basically torque. How much bending moment and torque this shaft is carrying, and it tells you the yield strength, the ultimate tensile strength, and endurance limit. Why did I tell you so many stress property? Can someone tell me why did I tell you this and this? Can someone tell me? Are they necessary? No. They are useless for the problem. So those numbers are there just to make you confused, to test you, to see if you understand how to solve the problem. For now, for static loading, we never use ultimate tensile strength, we never use endurance limit. They should be used later on when we talk about fatigue. But in the current model that we're using, we have three models: shear stress, strain energy, distortion energy. They only use Poissons ratio and yield strength as our coefficients inside the equation. So this is just to make you think, wow, why the professor gives me those numbers? Okay. So if you are tricked by me, then you maybe made a mistake. Okay? So the first problem is to determine the principal stress. Can someone tell me why do we need to solve for principal stresses? Someone? Very simple reason. Why do we solve for principal stress? Anyone? Don't be afraid to tell the wrong answer. That's fine. Try it.
So we can calculate. So we can use the max stress model.
Yes. So we can use the model, because in the model we have all the S. S stands for the principal stresses. So that's why in the first small problem we need to determine the principal stresses. Very simple reason. Yes, thank you. Okay, so did I introduce how to solve it? No? Do I have solution? Do I have solution for this? Ah, yes. Good for me. So happy. Okay, so if you put this down in the your solution sheet, if you write it down in this way, then you're in good shape. Yeah. You can just solve like this. Totally no problem. So what I did was I determined what would be the stress and shear stress due to moment and torque using the equation that we know. Can someone tell me, is this equation always correct if we are solving some other shapes? Is it correct?
No.
Yeah. Your answer is right. No. We have this equation only because we determine the area moment of inertia of a shaft. So the cross section is a circle. We calculate I and J. So for the circular area, I and J can be derived, and we use it to get those equations at the end. So whenever you use an equation, you must understand, can I use it? That's the most important thing. The next thing you need to do is be careful on solving. That's it. So just plug in everything, you get 188 megapascal for this normal stress. You get 113 megapascal for the shear stress. Sorry. Then I draw the Mohr circle, and I was calculating the maximum shear stress. The maximum shear stress basically is right here, and the maximum, right? And this is basically the radius of the circle, and the way, you don't even need to memorize the equation. Just, if you have figure like this, how you should be able to calculate the radius, right? I use the triangle right here. So the height right here is 113. The width right here is half. It's half of 188. So half of it, and then square, sum, square root. That's how you calculate radius. And also, after that, if I have radius, what I need to do is to determine this point. This point is basically half of it, so it's 94.3. So this point plus the radius, you got S1. This point minus S1, minus radius, you got S2. So I didn't try to write down the equation and then try to plug in. I basically derive while I'm solving. Okay, so what's the next question? The next question was, safety factor will be greater or smaller. What do I mean? Safety factor will be greater. Oh, okay. So I want you to calculate the safety factor, but is it greater than a value or smaller than a value? And what's the value? Something like that. So how do you do it? I told you to use maximum shear stress model. So what is maximum shear stress model? Basically, the maximum shear stress, tau max should be smaller than half of the yielding strength. And also you put your safety factor at the bottom. So what I want you to solve is basically this. So you should say the safety level or safety factor is smaller than a value right here. So this is what the problem is asking for. Okay, maybe the description was not very clear, but this is what the problem was about. So here, I did exactly the same thing, right? Just once you have this equation, plug in the numbers. So your safety factor is smaller than 0.8. So if you have a design like this, is it safe or not? No, because you should have a safety factor greater than 1. If you have a design with safety factor less than 1, it will yield. Okay? So this is indicating this is not a good design so far. And what's next? Where is it? Same question using and strain energy model. The next one using distortion energy model. So basically, I want you to plug in the equations. Okay? What we just introduced earlier. Just plug in. And then solve for n. So at the end, if you use maximum strain energy model, you will have a greater safety level. If you use distortion energy model, you have a safety level in between. So it means the first model, maximum shear stress, is the most conservative one. Sorry. I don't want to be video tape. Tighten. Okay. So, this is the most conservative one. When we are conservative, we believe we are not safe. So, the calculated safety level is lower. We should do better. But when we use the most aggressive one, our safety level, this is like the estimated safety level. It's higher. So we are aggressive. We think we don't need to improve too much. We are close to 1. Okay, so when you use strain energy model, you're more aggressive. If you use the distortion energy model, you are in between. Okay? So those are just plugging in. Okay? What's next? It's asking you to, based on those models, which one is most conservative and why? So exactly what I told you. The most conservative one is maximum shear stress model because the safety level is the lowest. So it's the most conservative one, the most conservative model. And the next question is it safe? It's not safe. It's not safe. So what should we do? If not, the yield strength should be greater than what? In order to reach a safety factor of 2. So when you are trying to find a greater yield strength, what does it mean? What does it mean? Change your material. Like right now, maybe it's a softer metal, and if the equation tells you you need a greater yield strength, that means you need a stronger metal. Basically, the equation can tell you. So we wish we can find a different material with some yield strength, and we wish that material will reach a safety level of 2. And in this one, let's use distortion energy model for the problem. So how do we solve it? Basically, we already have what is this? This is basically MSE stress because this is using the distortion energy model. So remember we have this. We said this is von Mises stress. Okay, did we calculate this already? Yes, we did. Von Mises is right here. Okay, this is von Mises stress. So in the problem 4, we already calculated 272. So over here, 272. This is basically von Mises stress. So the von Mises stress should be smaller than your yield strength. And over here, this is your safety factor. The problem said we are looking for a safety factor of 2. Just replace it by 2. And then calculate what's your yield strength. So at the end, you realize, okay, your yield strength must be greater than this value. You should find a material that has a yield strength greater than 524 here.
考试会问可以直接改直径吗？
Oh, I will tell you what I'm looking for. In reality, you can change diameter, you can change many things. But I will tell you what you need to do. You need to solve based on my question. Okay, so in this question, I asked you to find the material property that reach safety factor. Then you need to solve in this way. Okay, thank you for the question.